first live session on the course optimization in chemical engineering. So in this live session, based on your queries on the forum and some of our own consideration, we have decided to discuss the following. We'll briefly discuss about the evaluation and certificate policy for this course. These informations are also available on the website and you perhaps have gone through it. I'll just quickly go through that once. Then we'll talk about optimality conditions. We'll review this. And then we'll take a problem on optimality conditions where numerical solutions are required for solving the optimality conditions. You have seen that you are familiar with Lagrange multiplier methods and then KKT conditions. And you have seen that those KKT conditions or the gradient conditions that you apply on the Lagrangian function that you use in case of Lagrange multiplier method needs to be solved to find out the likely candidate points for optimum. Or in case of KKT conditions, we call those KKT points. So it may often happen that to obtain these KKT points, you have to solve a set of nonlinear equation where analytical solutions may not be possible. So we'll quickly go through an example where we'll highlight this issue. And we take help of in MATLAB function fsolve to solve such nonlinear equations. So let's quickly go through the evaluation or the certificate policy for this course. There will be a proctored exam, and the exam date is 24th April 2021. The exam will be held in 2 sessions, 9 to 12 in the first session and 2 to 5 in the afternoon sessions. So you have to visit the designated center to write this exam. Now, the evaluation policy as follows. The final score for this course will be a combination of your average assignment score and the exam score. Now, the contribution of the assignment score is like 25% of the average of the best 8 assignments that you submit. So if you submit all assignments, you'll be submitting 12 assignments for 12 weeks. Now, for the purpose of the computation of the final score, your 8 best assignments will be chosen. So 25% weightage will come from those assignments and 75% contribution will come from the final written exam. And the final score then will be average assignment score plus exam score. So if everything is scaled to 100, then say 25% from the, so the maximum contribution from the average assignment score may be 25 and the maximum contribution for the proctored certification exam may be 75. So the total possible score will be 100. Now, to obtain the certificate, you have to satisfy an eligibility criterion. So there are conditions on both assignment score as well as exam score. So the assignment score must be minimum of 10. So you must get 10 or above in the average assignment score. So as average assignment score out of 25, the maximum 25, you must get 10 or above. Similarly, for the maximum possible exam score of 75, you must get 30 and above. Note that both must be satisfied. So together it looks like 40 out of 100. But if you get, say, 40 from the exam score, but less than 10 in the average assignment score, so NPTEL will not issue you a certificate. So you must meet both the conditions. So I encourage you that you take the assignment seriously and please submit all the assignments. Now we'll review the optimality conditions. So basically what we'll do is we'll start with the optimality conditions for Lagrange multiplier methods. And you know that we'll start with an equality constant optimization problem. And then we'll see what happens if I put now, if I now only have inequality constants. And then finally what happens when you have both equality as well as inequality constants. So what you see on the screen is basically a general description of the nonlinear programming problem. So you have an objective function to be minimized. The objective function is in n variable. And you have a set of inequality constant. We have written the inequality constant as less or equal to type. If they are greater or equal to type, you can always convert in less or equal to type. Although strictly speaking, that is not required, but there is some convention. And to be consistent with one convention, I suggest that let us follow this particular convention, that we will put the inequality constant as less or equal to type. And then you have set of equality constants. You know that these inequality constants and equality constants together define the feasible region for the optimization problem, and your solution must lie within this feasible region. Now, a quick recap of the definition of the active and inactive constants. An inequality constant, we have defined the inequality constant, we have written the inequality constant as G less or equal to 0 type. It is said to be active at a feasible point X if the constant is satisfied as G equal to 0. So if the constant is satisfied as G equal to 0, we call this constant as active constant or binding constant. If the inequality constant is satisfied as G less than 0, we call it inactive or non-binding constant. Note that the constant is G less or equal to 0. So it can be satisfied being equal to 0 or being less than 0. So when it is satisfied as being equal to 0, we call this constant as active constant or binding constant. Otherwise, we call it inactive or non-binding constant. So by definition, equality constants are always active. So equality constants are always active at any feasible point. Note that these active constants restricts the domain of feasibility, but not the inactive constants. For example, here, let's say this is my optimal point, where you can see that this one, which is G1 equal to 0, the constant G1 is active constant.
Sir, please,
but
please share your
G2,
screen.
G3. They do not influence. Yes?
Share your screen, sir. Actually, students are not visible.
It's not visible.
No, sir.
Oh, so as of now, I have been talking without.
Yes, sir. Okay, sir. Fine.
Now is it okay?
Yes, sir. Fine, sir.
Okay, sorry about that. I think this part you missed the screen, but that's not important because this evaluation and certificate policy are already there on the websites, and we have talked about it. So it should be okay. So now let's quickly go through the portion that you have missed. So we are talking about the optimality conditions. Okay, we are going to review the optimality conditions. We'll first talk about the Lagrange multiplier method. So we'll talk about an equality constant optimization problem, then an inequality constant optimization problem, alternate forms, and then you combine these two to obtain the KKT conditions. So this is what is based on one of a query on the forum. And then we'll also talk about a problem where you will see that we need to take help of numerical methods for solutions of such KKT conditions or optimality conditions. Typically, we'll take help of fsolve function from the MATLAB and show you how to solve a set of equations that comes from optimality conditions to obtain the KKT points or the candidate minimum points. So a quick recap of the active and inactive constants. So inequality constants, we write as G less or equal to 0 type. So we'll follow this convention that inequality constant we always write as G less or equal to 0 type. So if the constant is satisfied as G equal to 0, we call it active constant. If it is satisfied as G less than 0, we call it as inactive constant. So following this definition, the equality constants are always active constant at any feasible point. So if you look at this figure, okay, given this that say candidate optimal point, your G1 is only active, but this and these are representing inactive constant. Another definition about regular points. So let us first talk about an optimization problem with only equality constant. A point x star that satisfies this equality constant, hx equal to 0, is said to be regular point of the feasible set if this function is differentiable and the gradient vector of all the constants, at x star are linearly independent. So the point x star will be regular point for this optimization problem if, of course, x star satisfies this and then the gradient of all the constants, that means gradient of hx at x star are all linearly independent. All the gradient vectors evaluated at x star are linearly independent. Linearly independent means that no two gradients are parallel to each other, and no gradient can be expressed as a linear combination of others. Now let's talk about optimization problem where you have both inequality constant as well as equality constants. So how do I extend this concept of regular points here? So again, let us say x star is a regular point, so that satisfies hx equal to 0. And then you look at this inequality constant is less or equal to type. So we extend the definition of the regular point for such optimization problem where both equality and inequality constants are present as follows. So a point to be regular here, the gradients of these constants as well as gradients of g equal to 0 constants must be linearly independent. In other words, if I say that if the point x star is a regular point, the gradients of all active constants must be linearly independent. So this is always active constants, this is always active constants, and g equal to 0 is also active constant. So regular points means that the active constants evaluated at x star, that means that regular point will be linearly independent. So now let's look at the Lagrange multiplier method. So we have an optimization problem like this, minimization problem. We want to minimize f of x subject to h of x equal to 0. Equality constant optimization problem. So the function may have n variables and there may be m number of equality constant. Now, the theorem that we talked about, which gives us the optimality conditions, note that this is valid only for regular points. So if x star is a regular point, if x star is a regular point and x star is a local extremum, that means local minimum or maximum of this objective function, which satisfies x star must also satisfy these equality constants, then there will exist m number of Lagrange multipliers such that this condition is satisfied. That means if x star is a regular point, it means that h of x star equal to 0 and x star is the local maximum or minimum of f, which also and x also satisfies this, and then there will exist m number of unique Lagrange multipliers such that this condition is satisfied. What is this condition? The gradient of the Lagrangian function will be equal to 0. So what is the Lagrangian function? The Lagrangian function is formulated by adding product of Lagrange multiplier and the equality constants to the objective function. So for example, let us consider I have two variable. I have an optimization problem with two equality constants. So minimize f of x subject to h1 equal to 0, h2 equal to 0. Both h1 and h2 are function of x. then the Lagrangian function will be L equal to F plus lambda 1 H1 plus lambda 2 H2. So if you have m number of constants, you define m number of Lagrange multipliers, then add to this objective function lambda 1 H1 plus lambda 2 H2 plus lambda 3 H3, so on and so forth, up to lambda m into Hn. Now, this condition states that the gradient of the Lagrangian is equal to 0. Now, the Lagrangian function is not only a function of decision variable now, but the Lagrangian is also a function of these Lagrange multipliers, x and lambda. So the gradient of the Lagrangian needs to be evaluated as del L del x as well as del L del lambda. So if you have n number of variables, so we'll have del L del x I equal to 1 to n equal to 0. Similarly, del L del lambda j, where j equal to 1 to m equal to this hj, but this is will be equal to 0 basically because h is equal to 0. So if you solve these two equations simultaneously, you will obtain, for this particular case, x1, x2 up to xn and lambda 1, lambda 2 up to lambda m, that minimizes the Lagrangian function. Now, since h of x equal to 0, that means the equality constant is being satisfied. So the same set of x1, x2 up to xn is also a solution to this optimization problem. So I repeat, if you have only equality constant optimization problem, you define the Lagrange multipliers and then set the Lagrangian function equal to 0. The gradient of the Lagrangian function to 0. Now the gradient of the Lagrangian function to equal to 0 gives you a set of equations. When you solve these equations, you get those stationary points or critical points which are likely candidates for minimum or maximum. Now, let's have inequality constant. Now we know that we can always convert this inequality constant to an equality constant by adding a slack variable. So g is less or equal to 0. So we can always add a non-negative term to g such that right hand side equal to 0. That non-negative term is known as slack variable. So I can add one term sigma square, where sigma square is greater or equal to 0, to make g equal to 0. So note that why sigma square is greater or equal to 0. Sigma square will be equal to 0 if this g is satisfied as equal to 0. So that means for active constants, you don't need any then slack variable because g is already equal to 0. The purpose of adding slack variable is to make the right hand side 0. So if it is already right hand side is equal to 0, you don't need any slack variable. But if g is satisfied as g is less than 0, that means constant is satisfied as g less than 0, then you must have non-zero slack variable. And you know that in that case, constant is satisfied as inactive constant. So when the constant is satisfied as active constant, slack variable is 0. When the constant is satisfied as inactive constant, you have a non-zero slack variable. Now, so such inequality constant optimization problem can be converted to this equality constant optimization problem. Note, for each G, I define one sigma. And then convert the less or equal to 0 type constant to equal to 0 type constant. Then it is same as the previous case. You define the Lagrangian function. So define as many lambda as the number of inequality constants. So, and then the product of this lambda or Lagrange multiplier and this equality constant now to the objective function to obtain the Lagrangian. Note that now the Lagrangian is not only function of decision variable x and the Lagrange multiplier lambda, but also this slack variable that has been added. So now you have to set del L del x equal to del L del x, del L del lambda, and del L del sigma. So you will have all these three partial derivatives of Lagrangian. So this. So you'll have the del L del xi equal to 0, del L del lambda j equal to 0. Note that del L lambda j equal to 0 will give you back this one. Gj plus lambda j square equal to 0. In case of equality constant optimization problem, corresponding to this was h equal to 0. Now, since g less or equal to 0 has been converted to g plus sigma square equal to 0, so this is obvious. And of course, these slack variables we have added must be non-negative. Because g is less or equal to 0, so you need to add some positive quantity to make it 0. And if g is already 0, you don't need that positive quantity. You need slack variable will be 0. So del L del x equal to 0, del L del lambda equal to 0, and del L del sigma equal to 0. Note that these slack variables as well as those Lagrange multipliers must be non-negative. Now, these derivatives will give you a set of equations which needs to be solved to obtain the minimum or maximum or extremum of this Lagrangian. And this extremum of this Lagrangian will be the extremum of the original function fx because they satisfy this constraint. Okay. Here, I would like you to point out this. This is precisely the reason why we are always considering g is less or equal to 0. Because Lagrange multipliers for g less or equal to 0 are non-negative. So lambda may be equal to 0 or lambda may be greater than 0. It can never be less than 0. If g is less than 0, lambda will be equal to 0. If g equal to 0, lambda will be greater or equal to 0. But if you can always write g greater or equal to 0 type as well, but then this line will be changed as Lagrange multipliers for g greater or equal to 0 are non-positive. So to avoid confusion, I suggest let us always convert the inequality constant as g less or equal to 0, and remember that Lagrange multipliers for g less or equal to 0 inequality constants are always non-negative. So now let us look at the alternate form. So what he did here is the inequality constant is converted to equality constant by addition of slack variable. And then we simply applied the first order necessary conditions. That means the gradient of the Lagrangian equal to 0. The first order necessary conditions. Now let's look at an alternate form where we do not need the introduction of the slack variables. So we are talking about this. We have this objective function subject to this g less or equal to 0 type inequality constants. So we have just seen that we have to the optimality conditions require del L del xi equal to 0. Before that, you of course form the Lagrangian. Note that g less or equal to 0 has been converted to g equal to 0 by adding these slack variables. And then we have just seen that the optimality conditions will be the gradient of this Lagrangian equal to 0, which will be basically written as del L del xi equal to 0, I equal to 1 to n. Del L del lambda j equal to 0, lambda j equal to 1 to p. Note that this is basically evaluated as this. Just take the derivative of this L with respect to lambda j. Non-negative slack variables and del L del sigma equal to 0. This is evaluated as 2 lambda j sigma j. 2 lambda j sigma j. Just take the derivative of L with respect to sigma j. And non-negative Lagrange multipliers. Now, look at now these two statements or these two conditions. These two conditions require us g plus this slack variable equal to 0 and non-negative slack variable. So basically this ensures that g less or equal to 0 is satisfied. So these two can be replaced by this single statement that let g be less or equal to 0, the feasibility condition, the g less or equal to 0. So these two conditions can basically be replaced by this single condition. Similarly, this del L del sigma j equal to 2 lambda j into sigma j equal to 0 can be replaced by lambda j gj equal to 0. So either g equal to 0 or lambda equal to 0. This is known as switching condition. So in other words, the introduction of this slack variable, which we are using just to make inequality constant, we are just to convert inequality constant to equality constant. Introduction of this sigma slack variables, which is required to convert this inequality constant to equality constant, is not necessary if the conditions related with this sigma j is replaced by this condition and this condition, which are known as feasibility condition and switching condition. So upon introduction of this feasibility condition, which says that g less or equal to 0 and lambda j into gj equal to 0, I do not need the introduction of slack variable. So basically these two are equivalent. So one is alternate form of the other. So one way to approach an inequality constant is to convert it to equality constant and then formulate the Lagrangian and set the gradient equal to 0, first order necessary conditions. Now the same conditions can be rewritten in a different manner by ensuring that G less or equal to 0 in my optimality condition itself. And then, of course, we need this switching condition. So while solving a problem, you can actually follow both the approach. Now, when in case of, let us once again summarize this alternate form. So we have this Lagrangian. You have this optimization problem corresponding to this. You have the Lagrangian, and then you have this gradient condition, the feasibility condition, the switching condition, and the non-negativity restriction on the Lagrange multipliers. So both this as well as this are synonymous. But note that these derivatives and these derivatives are incorporated in these two. So here you need only the partial derivative of the Lagrangian with respect to decision variable x. Okay. So summary, equality constant optimization problems. Introduce Lagrangian, introduce the Lagrange multiplier and write the Lagrangian. Set the gradient of the Lagrangian equal to 0. So the derivative of the Lagrangian with respect to decision variable x as well as derivative of the Lagrangian with respect to Lagrange multiplier. For inequality constants, we can write the alternate form. We have written the alternate form here, where we are not using slack variables. You can also write slack variables, but we don't write yet slack variables here. Let us write the alternate form. Now, when you sum up these two, you will see basically what you get is the KKT condition. So now, for a problem with both equality and inequality constants, you will have this set of conditions which needs to be solved to obtain the KKT point or this likely candidates for optimum. So you know the KKT conditions. Let's go through one more time. The Lagrangian, the gradient condition, set the derivative of the Lagrangian with respect to decision variable to 0. Feasibility conditions, both G less or equal to 0 must be satisfied, H equal to 0 must be satisfied. So feasibility check. Switching conditions, Lagrange multiplier corresponding to inequality constant multiplied by the inequality constant will be equal to 0. Non-negativity restriction of the Lagrange multipliers for the inequality constants. Note that inequality constants. So these are less or greater or equal to 0. Non-negativity restrictions on the Lagrange multipliers for inequality constants. And then this point we are talking about x star must be a regular point. That means the gradients of all the active constants must be linearly independent. So this is KKT conditions, which basically you can see the sum of those inequality constant, equality constants discussions that we had in our previous slides. Okay, so now we'll take up problem where it may not be possible for us to solve the KKT conditions or the conditions coming out of the Lagrange multiplier methods if you have only equality constants analytically. So when the optimality conditions cannot be solved analytically, that those conditions can be solved using any numerical method. Numerical method for solutions of nonlinear equations, such as Newton-Raphson method, Marquardt methods. There are several other methods as well. You will get to know some of these methods when you discuss nonlinear optimizations or nonlinear programming methods. For the purpose of this today's session, let me show you the use of MATLAB function fsolve for such cases. So what we'll do is, we'll take a simple example where there are, after applications of these nonlinear optimality conditions, we have, let us say, a set of 4 nonlinear equations which needs to be solved simultaneously. And we can do that using fsolve. Fsolve is a function that comes with the optimization toolbox. So it's, if you have access to optimization toolbox, you'll have access to fsolve. Now we have access to optimization toolbox, so you also have access to fsolve. So fsolve is basically a part of optimization toolbox. It's not the part of the basic MATLAB distribution. It's a part of the optimization toolbox of the MATLAB. So the minimum syntax that is required is this. Before that, this fsolve function will solve a problem such as f of x equal to 0, where f of x basically represents a set of functions. So it will return a vector value. F of x will return a vector value. It's like, say, f1, okay, or f1 equal to 0, f2 equal to 0, f3 equal to 0, f4 equal to 0, so on and so forth. That means a set of nonlinear equations. A set of nonlinear equations in x can be written like this way, in the vector notation. Here x is also a vector. Let us say I have x is a vector of 4 components, x1, x2, x3, x4. So I may have f1, which is a function of x1 to x4 equal to 0. I can write like this. Then f2, f3, f4 all equal to 0 like this. So fsolve can be used to solve such a set of nonlinear equations. And please look at MATLAB. In the command prompt, type help fsolve and then hit the return, and then you will get appropriate help for the use of fsolve command. The minimum syntax that is required is this. X equal to fsolve. Fsolve is the name of the function, and argument of this fsolve is fun x0. Fun is the name of a function which describes this set of nonlinear equations you are going to solve. And this one basically represents x0 basically represents the initial conditions. Sorry, initial guess. We won't say initial condition, initial guess. So to solve a set of nonlinear equations using fsolve, the first thing is to write the function fun. You can give any name you want, which will represent the system of nonlinear equations. Let's say, if I have 2 equations, I'll write like this. Function f equal to my fun of x. You can give any name you want here. So this will be the output that will be returned. So you write f of 1 equal to right hand side, you write f of 2 equal to right. So let us say here it is x1 square plus 2x2 square. Here maybe x1 to the power 4 plus x2 cube, so on and so forth. So basically, you follow this syntax to write the nonlinear equations that you have. If you have 4 number of equations, you write f of 1, f of 2, f of 3, f of 4, so on and so forth. There is no limit on the number of such equations. And then you just call the solver fsolve with initial guess. Let us say I have these 2 variable problems. So initial guess for x1 equal to 1, initial guess for x2 equal to 2. So x0 vector is represented like this. And then I just call fsolve with the arguments of this function, which I am defined, and x0, which is defined like this as initial guess. X is the vector that will contain the solution to this problem. That means, what is the solution to the set of nonlinear equations? So x will contain the solutions here. For this particular problem, 2 variable problem, so x will be a vector with 2 components. So this is how fsolve needs to be used. Let us now take this simple example. Yes.
Sir, there are some questions on the YouTube live chat section. Would you mind if we narrate them out to you?
I can see that. Okay, let me complete it, and I can see that. I have opened that as well.
So there has been one chat from the host as well. If you would check.
What is that? Can you tell me?
Sir, it is for the closure of the session within the next 5 minutes due to the time limit.
Okay. So let us have this function which needs to be maximized subject to this inequality constant. Let us say I convert it to equality constant and form the Lagrangian. So del L del x1 equal to 0, del L del x2 equal to 0. So this will be del L del u equal to 0. And this will be del L del s equal to 0. So this equation, this equation, this equation, and this equation, these 4 nonlinear equations needs to be solved simultaneously. I can use fsolve. So I call, let us define the vector x. So x of 1 is, let's say x1, x of 2 is x2, x of 3 is u, and x of 4 is s. So then you can just write like this, right? This is the usual syntax. So now I define that function, my function. So f of 1, f of 2, f of 3, f of 4. So I'm solving these 4 nonlinear equations simultaneously. And then you have this initial guess. And then just call the solver fsolve, and you obtain this solution. So x1 equal to 1.732, that means root 3, right? So x1 equal to 1.732, x2 equal to 1.732, x3, which is basically the Lagrange multiplier u, and that is 0.5, and this is last one, s, the slack variable is 0 basically. It's very, very small, is 0. So this is how you can find out the KKT points or the likely candidate points that satisfies all the optimality conditions. So this is what I had to talk about these optimality conditions. So there was a question on whether MATLAB will be, one can use the MATLAB, will we be provided to use the MATLAB during exam? Unfortunately, what I know that there is no such provision at the point of exam. While you write exam, there is no provision of using the MATLAB. So you won't be able to use MATLAB during exam, and the questions will be so set that it won't be, you will not need MATLAB software to solve any problem. Okay, so that's the time we have for today. So please ask questions on the forum, and we'll get back to you on the forum, as well as we'll respond to your questions in more detail in the next live sessions. So thank you for joining today.